variation of pressure with temperature and variation of volume with temperature. Both of them can be plotted on graph. Suppose if we calculate the pressure at different temperatures by keeping the volume constant, and if you draw a curve between pressure and temperature, we will get a straight line shown in the figure, a straight line graph shown in the figure. When it is extended backwards, it meets the temperature axis at minus 273.15 degrees centigrade, minus 273.15 degrees centigrade. Similarly, if you measure the volumes at different temperature by keeping pressure constant and draw a graph between volume and temperature, you will get the same graph, a similar graph. So, in the case of volume temperature graph or pressure temperature graph, the graph is a straight line which meets the temperature axis at minus 273.15 degrees centigrade. At this temperature, according to the figure, the pressure becomes 0 and the volume becomes 0. From the graph, what we notice is the pressure becomes 0 and the volume becomes 0 at minus 273.15 degrees centigrade. From graph, we have noticed that the pressure becomes 0 and volume becomes 0 at minus 273.15. We can also prove it from the equation. We have Vt is equal to V0 into 1 plus alpha t, where alpha is 1 by 273.15. Hence, by substituting this value, we will get V at minus 273.15 is equal to 0. Similarly, Pt is equal to P0 into 1 plus beta t. By substituting the value of beta, which is 1 by 273.15, we will get Pt is equal to P0 into 1 plus t by 273.15. By substituting t is equal to minus 273.15, we will get Pt is equal to 0. That is, pressure at minus 273.15 is equal to 0. What is meant by the pressure becomes 0? The pressure becomes 0 and the volume becomes 0. If the volume is to be 0, then the matter should disappear, but it will not happen. What happens is, as we reduce the temperature, as the temperature is decreased, at some temperature, the substance will be converted into liquid or solid. So, the substance will not be in gaseous state at this temperature. At minus 273.15 degrees centigrade, substance will not exist in gaseous state. That is the meaning of pressure becoming 0 and volume becoming 0. Basing on this property, that pressure and volume becomes 0 at minus 273.15, a new scale of temperature is devised, that is Kelvin scale of temperature. We take this state minus 273.15 as 0 Kelvin, and each degree in the new scale will be taken equal to 1 degree centigrade, and a new scale of temperature is constructed. So, the temperature of ice becomes 273.15 degrees Kelvin and the boiling temperature of water becomes 373.15 Kelvin. In Kelvin scale, the temperatures of ice and steam are 273.15 Kelvin and 373.15 Kelvin. So, this is how a Kelvin scale of temperature is devised, and the relation between Kelvin scale and Celsius scale is given by capital T is equal to small t plus 273.15. Capital T is equal to small t plus 273.15. Capital T is Kelvin temperature and small t is Celsius temperature. Kelvin scale versus Celsius scale, the relation between Kelvin scale and Celsius scale. On the left side, we notice Celsius scale minus 273.15, 0 degree centigrade, 100 degree centigrade. On the right side, we notice 0 Kelvin, 273.15 Kelvin and 373.15 Kelvin. So, minus 273.15 degrees Celsius is equal to 0 degrees Kelvin. The two temperatures are equal, and 0 degrees centigrade or 273.15 degrees Kelvin is the same temperature, or 100 degrees centigrade is same as 273.15 Kelvin. The relation capital T is equal to small t into 273.15. So, by if small t is 100, capital T is 373.15 Kelvin. If small t is 0, capital T is 273.15 Kelvin. If small t is minus 273.15, then capital T will be equal to 0. This is the relation between Kelvin scale and Celsius scale. Boyle's law. We have already studied this law in earlier classes. We know that pressure is inversely proportional to volume at constant temperature. Pressure is inversely proportional to volume at constant temperature. Generally, we plot pressure on y-axis and volume on x-axis. And if we draw a graph between pressure and volume, we will get a graph shown in the figure, which is a rectangular hyperbola. Like this, we plot the relation between pressure and volume on a graph and we observe a rectangular hyperbola. Boyle's law can also be written as PV is equal to constant. PV is equal to constant. This constant depends on the nature of the gas, mass of gas and its temperature. So, the constant in Boyle's law depends on nature of gas, mass of gas and temperature. Real gases do not obey Boyle's law, but Boyle's law is applicable at low pressure and high temperature. Boyle's law is applicable at low pressure and high temperature. Charles' laws. Constant pressure law. Constant pressure law. The volume is directly proportional to absolute temperature. This is Charles' first law. This relation is obtained when we measure the temperature in the Kelvin scale. When the temperature is measured in Kelvin scale, we notice that the volume will be proportional to temperature. So, at constant pressure, the volume is directly proportional to the temperature in Kelvin. So, V is proportional to T, or if the volumes at two different temperatures are V1 and V2, then V1 by T1 is equal to V2 by T2. This is the mathematical relation obtained from Charles' law. Charles' second law. This is constant volume law. Constant volume law. The pressure is directly proportional to absolute temperature. The pressure is directly proportional to absolute temperature at constant volume. At constant volume. So, the relation can be written as P is proportional to capital T. The pressure is directly proportional to Kelvin temperature, or P1 by T1 is equal to P2 by T2. P1 by T1 is equal to P2 by T2. Ideal gas equation. Actually, it is PV is equal to nR. Let us derive this relation. Let us take a gas whose initial state is P1 V1 T1. That is, we are taking a gas at a temperature T1. Its pressure is P1 when volume is V1. Similarly, when this gas is heated to temperature T2 and its pressure is P2 and volume is V2. So, we are considering a gas initially at P1 V1 T1 and finally on heating its state is P2 V2 T2. Now, the relation between these two values, between these two states is obtained, can be shown as P1 V1 by T1 is equal to P2 V2 by T2. P1 V1 by T1 is equal to P2 V2 by T2. Let us apply the gas laws and derive this relation. Now, let us take the initial state of the gas. It is described with P1 V1 T1. Now, let us suppose the temperature is kept constant and the pressure is changed from P1 to P2. Then the change in volume is say from V1 to V. So, at constant temperature, if the pressure is changed from P1 to P2, suppose the volume changes from V1 to V, then we can apply Boyle's law. From Boyle's law, P1 V1 will be equal to P2 V. P1 V1 is equal to P2 V. This relation is obtained from Boyle's law. Now, let us take the next transition. From the transition P2 V T1 to P2 V2 T2. That means, let us suppose the pressure is kept constant. The pressure is kept constant at P2 and the temperature is increased from T1 to T2. The temperature is changed from T1 to T2. Then the volume changes say from capital V to V2, capital V to V2. Since this transition is taking place at constant pressure, we can apply Charles' law. So, we get the relation V by T1 is equal to V2 by T2. We get the relation V by T1 is equal to V2 by T2. Derivation of ideal gas equation. We have obtained the relation P1 V1 is equal to P2 V. We have obtained the relation P1 V1 is equal to P2 V by applying Boyle's law, and by applying Charles' law we got the relation V by T1 is equal to V2 by T2. V by T1 is equal to V2 by T2. From the relation P1 V1 by P1 V1 is equal to P2 V, P1 V1 is equal to P2 V, we get capital V is equal to P1 V1 by P2, P1 V1 by P2. From the relation V by T1 is equal to V2 by T2, V by T1 is equal to V2 by T2, we get V is equal to V2 by T2, V2 by T2 into T1. So, equating both the values of V, we get P1 V1 by P2 is equal to P1 V1 by P2 is equal to V2 T1 by T2, V2 T1 by T2, or by rearranging we get P1 V1 by T1 is equal to P2 V2 by T2, P1 V1 by T1 is equal to P2 V2 by T2. Since P1 V1 by T1 is equal to P2 V2 by T2, this relation can be written as PV by T is constant. So, PV by T remains constant. This constant is taken as small r. If we take PV is equal to small r into T, the value of small r depends on gas, it depends on gas. Here V is the volume of 1 gram of a gas and r depends on the gas. This is gas constant. Small r is gas constant. Here V is volume of 1 gram of a substance and small r depends on the gas. Instead of small r, we take capital R. The relation can be taken as PV is equal to N into capital R into T, where N is the number of moles of gas, V is the volume of N moles of gas, and capital R is constant for all gases. It is called universal gas constant. Universal gas constant. So, the constant can be replaced either with small r or with N capital R. Capital R, universal gas constant. Universal gas constant capital R. From the relation PV is equal to nRT, for N moles of a gas, this law is valid, where N is the number of moles of gas. It can be calculated from the relation small m by capital M, where small m is mass of the gas and capital M is molecular weight of the gas. Small m is mass of gas, capital M is molecular weight. Capital R is universal gas constant. Capital R is universal gas constant. This is constant for all gases. It has same value for all gases. So, that is why it is significant in gases. In the study of gases, this value is significant because it can be applied to all gases. Evaluation of capital R. Evaluation of capital R. 1 gram mole of any gas, 1 gram mole of any gas occupies 22.4 liters at STP, 22.4 liters at STP. 22.4 liters is called gram molar volume, gram molar volume. For 1 mole of a gas, the relation is PV is equal to RT. For 1 mole of a gas, PV is equal to RT, where R is equal to PV by T, PV by T. So, we can substitute the values of PV and T and can find the value of R. P is the pressure. Atmospheric pressure is 76 centimeters. Atmospheric pressure is 76 centimeters of mercury. So, its value is 76 into 13.6 into 981 dynes per square centimeter. In CSS system, the value of atmospheric pressure is 76 into 13.6 into 981 dynes per square centimeter. We know at STP the volume is 22.4 into 10 to the power of 3 cubic centimeters. 22.4 liters. 1 liter is 10 to the power of 3 cubic centimeters. Hence, the volume is 22.4 into 10 to the power of 3 cubic centimeters. STP means standard temperature and pressure. Standard pressure is atmospheric pressure and temperature is T is 273. 273.15, of course, it is taken as 273. Now, the value of R is calculated. 76 into 13.6 into 981, that is pressure, into 22,400 volume divided by 273 temperature T. Using these values, we can evaluate the value of R. On evaluation and calculation, we will get the value of R as 8.318 into 10 to the power of 7. 8.318 into 10 to the power of 7. This is x per mole per Kelvin. X per mole per Kelvin. Or it can be written as 8.318 joules per mole per Kelvin. Joules per mole per Kelvin. Joules per mole per Kelvin. The number of molecules in 1 gram mole is Avogadro number, which is 6.0225 into 10 to the power of 23. The number of molecules in gram mole is 6.0225 into 10 to the power of 3, which is Avogadro number. We have capital R is equal to N into Kb, where capital R is universal gas constant and K is Boltzmann constant. K is Boltzmann constant. So, we can evaluate Boltzmann constant from the value of capital R. On calculation, we will get Kb as 1.3805 into 10 to the power of minus 23 joules per Kelvin. 1.3805 into 10 to the power of minus 23 joules per Kelvin.